So welcome to today's lecture, and today we are going to move a bit from finite element code and go into how to visualize the results of different phenomena. And it could be finite element, it could be also other things. And what we are going to use for tool for this is software called ParaView, which is developed at the Sandia National Laboratories in the US. It's a large-scale visualization tool, so it can be used from both on your desktop, but also on supercomputers where you can distribute the visualization over several nodes and servers. So it's a powerful tool, but it's quite useful even for small problems, as I will show you. So I will give a brief outline of the project or the application, how it's used. I will not go through batch scripting, but it can be noted that ParaView has a built-in Python interpreter as well. So you can use Python to save your visualizations. You get a standalone Python file that loads your data and remembers all your settings. And also, I won't go through how to visualize large models. So, what is ParaView? So it's an open source application, so it's free to use. So you can just download it from the web and use it. It also supports different platforms, so you can run it on your Mac, you can run it on a Linux machine, on a Windows machine. It also supports distributed computing, so you can distribute the visualization algorithms that you use. You can distribute over multiple servers. It has an open, flexible, and intuitive user interface. It's intuitive when you have learned it, so you need to kind of understand the basic concept before it makes sense. It's a bit complicated in the beginning, but I will show you with some examples how you work with it. And it's also an extensible modular architecture, so it can support plugins, and you will see also that the entire application consists of several hundreds of plugins that do a certain thing that you can connect together to achieve your visualization. So these are some examples of visualizations that you can achieve using ParaView. It's very common in fluid mechanics that you do streamlines, so you can visualize results of virtual wind tunnel experiments. But it can do finite element codes. It can also do molecular visualizations and stuff like that. So it's very broad. So it's quite heavily used. So it's downloaded over 130,000 times per year. It's used by academic, government, and commercial institutions. It has also won several awards for best tools in high-performance computing. So you can basically put anything into this application, regardless of size. So you can see here some landmarks of the usage here. 6 billion structured cells, 250 million unstructured cells, and you see 6.3 billion unstructured cells is in a derived tool called Catalyst. So you can handle large sets of data. ParaView is not it builds upon several libraries. So at a low level, it uses OpenGL, which is the hardware accelerated graphics API that is used to talk to graphics cards. MPI is for parallel computing, and so on. But the most important library is what comes above these. It's called VTK, or Visualization Toolkit. This is a C++ library that implements most visualization algorithms that currently exist in research. So this is kind of the foundation layer of ParaView. Then you have the ParaView server, which is you can use if you want. it's used for distributed computing, so you can distribute over several servers to divide up the load. And on top of that, you have the user interface library, which is built on Qt. So you can see here that Qt is well used in other environments as well as not only Python uses Qt. So this is a ParaView is a C++ application, but it uses Qt widgets. And then you have the ParaView client, which is what we are going to show you today. But it also has a standalone command line Python interpreter called pyvtk that can be used to run your script standalone without the user interface. And there are some other tools as well. There is a web-based tool of this called ParaWeb, and a specialized tool in Catalyst. And there's also several applications that has been built by customizing ParaView to do something a bit different. So the ParaView is a basic application we want to use. Here's some history here. So it started as 2000, so it's a relatively modern application that has developed during the years. And also now one important thing is it supports OpenGL 3.2, which is a modern way of using hardware-accelerated graphics, a new API that improves the performance significantly. And there's some funding here. But what is visualization? So I think this picture tells it all. So usually when you do finite element codes or another simulation application, the results of the simulation is written down in files that contains floating point numbers or any kind of numbers. And what you want to achieve is a way for the human perception to kind of understand these numbers or the process that you have simulated. And the visualization is the kind of task of going from numbers to something on the right side here, which is the visual representation of these numbers. Just going to get my. So in this case, this is a wind tunnel simulation of the space shuttle. ParaView uses a number of standardized data types that is kind of the primitives of its visualization algorithms. So if you start from the top left here, this is kind of one of the most basic visualization data type is a rectilinear grid. So a grid consisting of rows, columns, and depth columns, so to speak. There's also a non-uniform rectilinear grid in which here you can set that it should have different steps. It's varied grid sizes here as well. And also a special form of the rectilinear grid is the curved linear grid. Basically the same kind of structure, but you specify a curvature. And here the kind of properties of these grids are that you can determine exact points here by specifying some kind of row column ordering. Something that is very common in CAD systems is the Polydata or the unstructured grid, which basically has polygons connected together that creates faces or surfaces to build up a structure that you can visualize data on. And then there is also the unstructured grid, which is very common in finite element code, so that you have blocks that are connected together, but they don't have a there is no method of getting to each element except for looking at the element and looking at the node topology. So these are the building blocks of ParaView. So what you want to do when you work with ParaView is get the data read into ParaView into one of these or more of these primitives. And then you can use the visualization algorithms on these basic primitives. There are some documentation here on how to use ParaView. There's also a lot of YouTube videos and guides that you can follow. There are very good tutorials on the ParaView website. So if you want to go deeper into this, it's a good idea to go and look at these. There is also a very good book, the ParaView guide, which you can buy online. So instead of doing a lot of PowerPoint slides, I'll try to show this application instead. It's a bit small here, but you have it's the basic layout that in the middle here you have the visualization screen where your visualization will happen. On the left side here you have something called a pipeline browser, and all the visualization in ParaView is built on a pipeline. So you load your data and you attach the data to a filter, and then that filter generates new data, and then you connect filters together into a network. And the data flows from top to bottom. And below here you have this is the properties area. Here is where you modify your filters, your objects, to behave in the way you want. I will show just basic interaction here. So there are two major menus here. There's something called sources, and sources are objects that can be generated from scratch within ParaView. Filters are things that you can affect the visualization in some way. It can be that you want to slice, you want to cut, create streamlines. So you take your data and put it through a filter. And I can show you here alphabetical. This is all the filters that are available in ParaView. So you see, this is can do most of the things that you need to do in visualization. So just to show you, I will create a geometric shape here. I will create a cylinder. And you see here, I created a cylinder, and you have this cylinder object here. But you see, nothing is shown by default. And the reason for this is that many of the objects you want to load into ParaView are really huge. So you don't want to kind of display them directly. You want to perhaps do some processing, set some data, and do some filtering before you show anything on the screen. So you can see also there is a green button here called Apply. And every time you add something to your pipeline, you need to press Apply to make it visible. Now you see here that I got a cylinder here, which I can click on the mouse here and rotate it over the screen. I can also in this I can show you show the properties here. You can see the resolution here, 6, that controls the number of sides in my cylinder. And you see also if I change it, nothing happens. If I want to change it, I have to press Apply again. Now you see I get a bit more sophisticated cylinder. I can also change the representation here. So currently it's displayed as a surface model, but I can also change it to a surface with edges here. So here you can see the edges or faces that this cylinder consists of. I can display it as a wireframe, so only the lines. I can display it as points. I can, if I have large objects that I don't want to display, but I want to change the viewpoint, I can use the outline representation as well. Feature edges is the kind of edges of your model, but we will go with surface here for the moment here. I can change the color here, and here you can also select, if you have data embedded in your ready data, you can change the field that should be used to color your model. But I can change here, I want to have a red cylinder. Okay, I get the red cylinder. I can also do it somewhat more plastic-like. So if I add specular here, you can see that I get a bit, it's more plastic surface here. I can do it transparent, so I can make it see-through here as well. That can be useful when you do different visualization, that sometimes you want to see through some kind of part of your visualization. Then you can use the opacity slider here to change, make it completely solid or make it transparent. I can also, on all my objects, I can add a grid here. So it's similar to what you can do in MATLAB and Matplotlib. You can add an axis here. I can disable those. So this is now, of course, cylinders is not so much to look at. So usually you have data that you read in. There's also ways of on top here. There are some controls here to change the view here from different axes here. And if you zoom out and you want to kind of make sure that model is shown, you can zoom to data and it will kind of zoom in and show your data here. So also there is no new function in ParaView. So if you want to start from scratch, you do something called reset. And that is a reset session here, this arrow here. If I press this one here, it asks you, do you really want to erase everything in your visualization? Yes. And now it erases everything. So now I will open an example data set just to illustrate what you can do with this. So open examples. See if this one. Yes. So this is a simulation of heat flow in a. So this is difficult to see here. Let's see if I can just show. You can see it here. There is a fluid here, and there is a heat source here in the middle, and then there is a flow simulation here that has been performed. So we will try to visualize the field inside this tube here. So if we go to surface again, you can see there is a hole here, and now we want to color this, change the color of this. You can see here that I have a lot of variables here that are part of my model. I can just make sure that I select all of them like that. And now you see it's colored by gray color and surface like this. So I want to kind of see if we can color this object or this simulation here with the temperature. Then I can go down to colors here. I change the temperature here. And now you see here that it's kind of blue, cold on the outside, but you can see here inside here there is a red part here, and that is the heat source here. So it's heated here. So how do we kind of make this visible in some way? What we could do is we can slice this model so we can look inside it, and that we can do using the clip filter here. So we add a clip here, and you can see here that we got a clipping plane here. And I think we can accept the default clipping plane here. So just press apply. And now you can see here that we have sliced up our computational model. So you can see here that the temperature of the simulation here is displayed here. And now we don't want to see the cutting plane here, so we can just uncheck it here, so we just see this cut plane here. So, and then perhaps we want to change our coloring color scale. That we can do as well. So we can press on the coloring here, we press, there's a folder with a heart, and you can get different colors here. So let's take something that looks more like it's heat here. So black body radiation, apply. So now you see here that we have a full thing here. So suppose we want to show some flow line, how the field is flowing inside this model. We can do that as well. And now we will I will add, so now you see here that the original model is turned off. There is an eye here, and you can press this here, I can turn this on, and now you see it's completely black here. But what we could do is we can turn the original model on and make it transparent. So now you can see here that you see through the model here as well. What we can also do here, we make it very transparent like this. Yeah, we keep that. But now we want to do flow lines here. So we will visualize the flow inside this model. So what we can do then is we press the model here. We want to make the flow on the time model, not only from the clip, but from the original model. Then we do something called stream trace, and that will release streamers in the flow. So let's see, we want to do a point cloud here. So now it will release particles from this sphere here, and I will make the radius a bit 3.5. And then we do apply. Now you can see, oh, I removed my sphere here. And I don't want to show the sphere here. I can turn my. So now you can see here that the flow lines are flowing out from the heat source here. And what we want to do as well is perhaps make these streamlines a bit thicker. And what we can do is we can use a filter on those that is called a tube. And here we can just see what happens if we just apply here. And now you get the streamlines are visualized by tubes. And I think we will do them a bit smaller, like this. And perhaps we should set some axes here so you can see how the. So this is a simple way how you can use ParaView. But the big problem is to get your data inside. This was an example model, but you probably want to have your own data inside the model as well. So how can we do that? So let's do a reset here. Yes. So if you look at open here, the dialog box here, you can see here that ParaView by default supports extremely many input formats. But we are only going to use one. But when you're using it or want to use it in your own work later on, it could be a good idea to just look at what the support files are and use them. But we are going to use something called a Vtk file or .vtk. And that is a text-based file or binary file that contains your model. We are going to use Python to generate these models. So let's see if I can bring up Spider here. So what we are going to do now first is to load a data file here. So the data file I have here contains a vector field. And let's see if I can expand it here. Two vector fields, vec1 and vec2. And we are going to use something called pyvtk, which is a special module that can write these VTK files in a structured way. So here I read in the data here. So it reads the XY coordinates and also the vector fields U, V, W. So there is a method in NumPy called load text that can load text-based data. Let's see if we can see this file here. it's a really large file, so that's why it takes some time to read it in here. So hopefully. So this is a text file containing floating point numbers. And the first two rows here are just, it says how many rows, columns, and depth the grid is made out of, which variables, x, y, z, and u, v, w, which is the vectors. And then the data comes here. You can see it's really long. So we are going to read that in, and we are going to convert this to points and vectors. So we create one array that contains the points and one containing the vectors. And you can see here I use index notation here to get all the rows, the 0 and 1 and 2, the three first columns go to the points, and the last columns go to the vectors. Then I create something called point data. And point data is the data structure that is going to, the data that is going into each point in the grid. And you can see here I have two vectors here. I have Vtk vectors here, vec1, and I put vectors in here, and the second vector here, vec2. So I put basically the same data twice into the point data. So I have two vectors in the in each point. And then I create Vtk data here, and then I have to tell them what kind of structure is this going to be. And this is a structured grid with its 96 rows by 65 by 48. And then I assign the points here for the coordinates, and then the point data here, the data that goes into each point. And then I do data to file u, v, w, and I want it to be an ASCII file. So this reads the data here, converts it into what we wanted. We can visualize that into in ParaView. So the UV dat file, that is something that ParaView doesn't know, and we create it into something that ParaView understands. So when I run this here now, hopefully it will run. So it's reading now from, you can see it here, reading from U data, converting to points. And I think it's done now, yes. So now it created a file called UVW here. And if we look at that here, it's also large, so hopefully it will be a bit quicker. Yes. Let's see if we do. These are, it's a 25 megabyte file, so it should be. Could be that Spider is a bit. Yeah. So this is how the final file will look like. So it's a bit more structured. So VTK data file, really cool data. Okay, we hope that it is. Data set with structured grid, dimensions, so and then the points are listed here. So let's go back to ParaView and see if we can load the data in. So we have our VTK file here. So let's load it. And now you can see that ParaView already loaded the file. So ParaView is in C++, it's very much faster than perhaps reading a file in Spider. You do apply. So now by default, it just shows you the outline of my data here. So let's say that we want to see the surface here, like this. And we want also to just see how the data is laid out here. So you can see here that this is the data structure here with the grid. So it's kind of a bit smaller element sizes here at the edges here. So let's see if we can color the edges here. If we color by vector here, so we just see the magnitude of the vectors here, color the surface here of the magnitude of the vectors. But what we really want to see is actually the vector field here. So what we can do now is we make this model a bit transparent here, like this. And then we create something called a glyph visualization. And the glyph places a oriented symbol at each vector in the data. So let's see here if we can do we do a 2D glyph here, and we orient it according to the vector. Let's see here. We scale the magnitude. Let's see what happens here. So now you can see here that I got a lot of arrows here. And they're oriented in the direction of the vector field. So apparently this is a flow going from left to right here. I can make them a bit smaller. Like this. It's also possible, so by default, ParaView places them randomly in the field. So if you want to have a vector on each of the nodes in the, you have to set all points. And now you can see, now you get an arrow on each point of in the vector field, which is kind of a bit hard to see here. So that was not good. We have to all points, every nth point. We set every 10th point. And you see here that they are distributed regularly. But usually this uniform distribution here is quite good, like this. What we also can do is we can do, we turn that off. We can do streamlines here as well, like this. We do type point cloud. We put it here, and we make it larger here. And then we apply this here. And you can see here it releases streamlines into the stream, and we can have a bit more of these. We can take 500 like this. So these are released, and they are simulated flow through this vector field. And same thing here, I can add a filter here called tube. And okay, now I get a bit really large tubes here. Like that. So in this way, you can modify your data and visualize this data cube I had. And you can see here the visualization goes from the top here. So I read the data in. This is the base data. I can remove that and I get only the streamlines. And the data flows to the glyph here. These are the vector field. I can turn them on and off. And I can, from this data, I can also create a stream tracer here. And from the stream tracer, I created a tube here as well. So using this, you can kind of visualize anything. That was this one here. I do reset. In the next example here, I have an image that contains elevation data. And here I also create a point data here with scalars. And I say that this structure is 400 by 400 and attach point data to each point. So this is a two-dimensional data structure that I want to kind of make 3D. So I run this. And we can see here also, this is the image data from the elevation data. So this is an image of the elevation data in this data structure. And I create elevation Vtk. I open. Elevation. Apply. Now here I got my data here. What I need to do now is to switch to 3D. So now I have a three-dimensional plate here. What I want to do now is to warp it to take the elevation data and scale it to create a three-dimensional surface. So let's see here. Warp by scalar, so like this. And I will use the scalars inside my data to scale here. So let's see if we can, how to size it here. Apply. Now you see here I have extracted the height and so now I can look at the elevation in a much nicer way. Then I want to create a bit smoother here. You can see here it's a bit edgy here. And I can add a filter here. Generate surface normal, there it was. So surface normal, so normally when you visualize this data, you will get smooth surfaces, or not flat surfaces. So if you come look at here, you can see here that the entire visualization consists of smooth surfaces. And what you want is to kind of smooth that out to make it more that you don't see these surfaces like this. So what you do then is to generate surface normals. That means that it calculates the lighting by interpolating the vectors on the nodes instead of the surfaces. So now you see here that it's smooth and nice here. So we need to change the coloring here as well. We do more like something like this, and we make the surface a bit more shiny here as well. Sorry, I need to close my my children just came home, so that's why I needed to close the door. So you can see here that I got a really nice visualization of my elevation data. So that was elevation data. Let's reset here again. I think I skipped that one. So just to illustrate some of the data structures inside VTK here, you have, so you can create quite complex data structures. So Polydata, that is data consisting of nodes that form the kind of which the polygons connect. So the polygons here, these are topologies 1, 2, 3, 0, 1, 2, and 3. That is refers to 0, 1, 2, 3, and so on. Point data is the data you attach to the geometry. So it can be, you can attach them to the middle of elements. You can attach them to nodes or points. Cell data is also, it's kind of a finite element to cell, and to this you can connect fields and data as well. Let's see if we can. So this is example 1. So this is a very simple example here, just of a cube, and you see here that the data varies over the field here. So cell scalars are, the cells are the surfaces here, and these are given a value, each of the sides here, and the scalars are on each node. So you can see it interpolates here over the node here. This is an example of how you can use a function here to color a structure here as well. So you can calculate here using this function f here, the data here, and map that to a structured grid. So let's see here, example 2FSG. So you can see the grid here, and the values here in each of these data points were calculated using the function f. And also to finally illustrate that you can create any kind of data structure, any kind of geometry. You can use an unstructured grid that can consist of points, hexahedron, tetrahedron, polygon, quad, triangle, line, and vertices. So this is the general example 3. So here you can see that it created, there's a line here, it's difficult to see here, but there's also a point here. I will do surface with edges here. You can see here that it consists of different kind of geometries that are connected together, but all of these can have data attached to the nodes here. So let's take a 15-minute break, and I will get back and do an example that is more related to finite element and also the assignments you would do. So I will be back in 15 minutes. Okay, so now I'm going to show an example that connects more to your assignments. And in this case, we have plane stress problem, two-dimensional problem. I will just run it here so you can see the geometry and also what we're supposed to get in ParaView as well. So let's see here, we start with geometry. It looks something like this. So it's a metal sheet here with indentation here with spheres, whole indented spheres here. And there is a load pulling on the right side. The mesh is shown here. So it's a rectilinear grid with curved surfaces here. So it's not an unstructured grid. And here you can see also the von Mises stresses here in the structure. So in some way we need to kind of convert the data we have calculated here and create a Vtk file containing all of these things. So I have prepared a recipe for this, which I will do step by step now. So the first thing we need is to create the points that will be used in the Vtk export and the polygons. And unfortunately, the pyvtk toolkit doesn't take NumPy arrays as input, so we need to convert the NumPy arrays to lists, which is quite easy to do. So if we start with, so we want to create a points variable here. We take the coarse array, and there is a method on the array object called toList, which converts any array to a list. And then we need to create a polygons topology list. And the topology we have is in CalFem is 1-based. So we need to convert it to a 0-based topology. That is also quite easily done. So we create a polygons variable here, which is equal to mesh dot topo -1, and then we do a toList of that. So now we have the basic kind of structure that to be able to create our visualization here. We also need to create a vector field of our displacements because ParaView doesn't think in degree displacement arrays. It always works in vectors in certain ways. So you can attach vector data to a point, and you can attach. There is no kind of doesn't know the A vector, for example. So we do a list here, empty list displacement here, which is empty. Then we loop for I in range 0 to len A, which is a displacement vector, step by 2 like this. So we jump over our displacement vector. We know that the displacement vectors are kind of in pairs. So the first degrees of freedom is x displacement, the second y. So we jump over this in steps of 2. Displacement dot append, do np dot as scalar np. The reason we do a scalar here is because we want to kind of get the scalar values out here and not erase. AI plus 1. And then ParaView always want its vectors as 3-dimensional vectors. But as this is a 2-dimensional problem, we just set the third dimension to 0 here. And that should be all we need for that. So now we need to create the data that is going to be attached to the ParaView visualizations here. So we do a point data equals to vtk.point data. And then we take the vectors here that we want to connect. So the displacements are going to be attached to the node points. So the point data is vtk.vectors and displacement. Then we can give a name of this vector field as well. That could be good to kind of recognize it in ParaView later on as well. So that should be enough. So for the point data, we attach a vector at each point, and the data for these vectors are taken from the displacement list here, and then we name it displacements. Then we have our von Mises stresses. These are scalars. So we do scalars equals to vtk.scalars. On Mises, we calculated this here in our code here on top here. This is our Mises stresses, and we give that name as well. Mises. And we have vector. We have our principal stresses as well. Those are also vector fields. Vectors 1 equals to vtk.vectors. Vectors principal 1 equals to prince 1. We have vectors 2 vtk.vectors 2 like that. And then these scalars and these vectors are attached to the element midpoints. So they are not connected to the node. So then we have to create a variable called cell data that we call vtk.polydata. Points equals to points. Oh, sorry, I'm wrong. Cell data should be cell data, and it should have scalars, vectors 1, and vectors 2. So this is the cell data we want to attach, and then we have to create a data the element structure. So structure. So vtk.polydata. And then we can create everything together now. So we can do vtk data equals to vtk.vtk data. So we have a structure. We have our cell data. We have our point data. So first we create the data for the structure, points and polygon. We create a displacement list. We attach the displacement list to each point. We call it displacement. We create three vector fields, one scalar field and two vector fields. Name them von Mises, Prince1, Prince2. And then we create the cell data that we attach to every polygon here. So scalars, vectors, and vectors too. And now we have to save it to disk. So we do vtk data to file. What we call this? We call it exm6.vtk. And the format is ASCII. So hopefully I coded without any errors, so it should work directly. Let's see. What did it say? 9187. Let's comment out my visualization here. You have to spell as well. So we're trying to select one. Oops. Let's see if this works. All right, seems to work. Let's see if we have a VTK. Yes, we have a VTK and it's created today. If we look at that, so this is what it created here. So let's see if that can be loaded into ParaView. EXM VTK. Okay. So let's see if we can see what it's. Oh, it already did visualization here. So it seems to have been able to read our data in, and you can see that this is seems to be our structure at least. By default, it took the von Mises stresses here and visualized those. So let's see if we can change the color scale here. Like that. So now we want to visualize we have two more fields. We have a displacement field, and we can see here on the nodes we have displacement here as well. So let's see if we can add glyphs here. So that is a vector field, yes. So let's see if we can warp our structure. So there is a special filter called warp by vector that you can use to apply a deformation on a structure based on a vector field. So let's do that. and we work, and you see it already pre-selected displacement here. So let's see what happens. You just apply here. Yeah, we couldn't see that properly. So what we can do is we can enable our original structure here, and the work by vector, we say that this is a wireframe, and add it on top. And you can see here, we can color this by solid color here as well. Now you can see here that we have visualized our displacements here. And we can do, let's see here, we can stretch this a bit too much perhaps, like that. And we can make it a bit transparent so that we can see the other things as well. What we can do now is we want to display the principal stresses as well. And now we have to choose if we want to do that on the displaced model or we want to do that on the original model. We'll see, we do that on the original. We turn the displacement off. We select that we want to start with the undeformed model here. And then we do a glyph filter. And we do lines here. Let's see here, line. We use then we start with the principal one and scale the array with principal one. And we set the magnitude here. So let's see what happens here if we just apply here. Okay, that is a bit too much scaling, I think. So we need to calculate a better scale factor here. So we do that and we apply again. Okay, this is better, but it's still a bit confusing, and we want to show it on all points here. So now you see there is one arrow on each point. And we perhaps should color it by solid color instead. So now we have white arrows, but we do them a bit smaller, I think. Yes. So now we need, now this is the principle, the main principle or stress. We have the second one as well. Now we have to think about to scale them in the same, using the same scale factor, otherwise it will be a bit strange. So what we do now is we go back again and do another glyph here. We use line here as well. We use principle 2 this time, and we have scale with the principle 2. And we make sure we have every point. Let's see here. Okay, now it's a little bit too much. And we go back to the other glyph here and copy our scale factor here. Go into that one and we paste that one into here. Apply. So hopefully we should see, yes, there are 2 arrows here in each element. And we should make sure that we don't have a solid color on those 2 as well. So now we have the von Mises stresses here. We have to have an axis as well, like this. So now we have, I think we have visualized everything we wanted to visualize here. So that's good. There's not so much more we can do. We can of course, we can have display the displacement field as well here. What you could do, you could also apply the Mises stresses on the deformed mesh. That is, you can do yourself as an exercise. So that was this. For those doing a temperature problem or I will show how this can be done as well. So now we do a reset here. So another thing that is it's nice that we will be using here when you are doing the parameter study is that ParaView can handle if you name your files with a number in them, you can load them as a sequence. Let's see if I have an example here, a stress example. So this is actually from your assignment here, and there is on top of the screen there is like a CD player controls that you can move in time. So if we can move one step forward here, you can see that the structure changes here. And the scaling, the color scaling is based on all the values in the entire sequence. So 1.1 E raised to 7 here, E7, that is the maximum stress in the entire sequence. You can see here that we can compare the stresses to when the slot is widened here. And that goes also for the there is for the groundwater problem. Here you also have a slot here, and you can move in time when the slot is going deeper here. And then you can animate here as well. You can loop here, and it goes back and forth like this. So you can see here that ParaView is a quite powerful tool, and you can do a lot of can handle most things that you kind of require when doing visualizations. Another thing that I want to show you finally before we end here is that you can save your visualization states as well. So I do a reset here. If I now, let's see here if I can do my, not a good example. So let's see here, if I take the standard example here, open examples, discount reference here. Do a quick visualization here. That I want to visualize. Temperature, like this. I do a slice. Oh. So I did a short visualization here. I have access here. So I can save this now. File, save state. And what you can do here now, just to make it interesting here, is that you can save it as a Python state file. And let's see here if we call this testing, save. Okay. And we can open this file. So this is the file that is generated by ParaView in this state file. And you can see here that it creates a render view, it creates all the steps necessary to create this visualization again. This you can run on the command line, or you can run it, open it in ParaView. So you can go into this file, edit it. It's Python code. You can edit it, and you can open this in ParaView. So if I do reset now here, like this. If I load state testing, okay, it will do all the steps here, and also even make sure that the view is the same as I left it. So this is a way of saving your visualizations when you have put a lot of effort into creating this network. Save the state, and it will remember every state, and it will load the files as well that you have referenced in this state file. So that was what I wanted to show today. And do we have any questions?